we're scheduled to have a quiz today, I think, but we're not going to do that. So the first quiz that we'll do is what's listed as quiz 2. That's in 2 weeks or something. So today we're going to get into unit conversions, scientific notation, that kind of stuff. Before I do that, let's just do a little reminder of some of the stuff we covered last time. So without looking at your notes, does anybody remember? So remember talking about the 4 common misconceptions? Can anyone remember what the first of those was? Well, come up with any of them and I'll be happy. I'll probably be happy enough if you don't come up with any, but I'll be happier if you. Okay, so the 4 common misconceptions in this class. Ooh, the first one is related to gravity. The first 2 are related to gravity. That's not exactly it, but it. That's right. That's right. That's the first one. Yes. So the first one says heavier objects, or I guess the wording I used is gravity does not make heavier objects fall faster, than lighter objects. So gravity does not make heavier objects fall faster. Sometimes it is true that heavier objects fall faster if you drop 2 things at the same time. If you dropped a feather and an elephant off a building, well, you don't have to do that because we know the physics of it. That's good. But the elephant would hit the ground faster. It's not because the elephant is heavier, it's because air resistance affects the feather a lot more than it affects the elephant. And we'll talk about reasons why. But if you didn't have air resistance, or if you sucked all the air out of a room, made it a vacuum, and there was no air to slow things down, they would hit the ground at the exact same time. You'd let go of them and they'd fall exactly the same. So it's not because of the weight. Any differences in 2 things are just air resistance. And you can come up with a lot of examples where a heavier thing falls more slowly than the lighter thing. Okay, the second one is also related to gravity. Anyone remember what that one was? Don't look. That's the third one. Okay, that's an important one too. Yes. Okay, so the second one is the horizontal motion of an object doesn't change how gravity affects its motion. So if you shoot a bullet out of a gun horizontally, it still takes the exact same amount of time to hit the ground. It just hits the ground way out of your vision, and that's why that sort of doesn't, that doesn't really resonate with you for most people. And like at a Twins game, when you watch these people who throw baseballs really, really fast, it looks like these baseballs are almost a straight line. Well, the reason that they can throw them and they're almost a straight line when they throw them all the way across is because they throw them so fast that the thing only has time to drop this much or whatever by the time it's gotten all the way across the field, But it's still curving down the whole time due to gravity. So the horizontal motion of an object
horizontal motion the same as angular momentum?
No, that's different. So angular momentum has to do with, think of it as having to do with changes of orientation. And so we won't get to that until the last topic in this class, one of the two last topics in this class. For now, almost the whole semester, we're going to think of things as particles, which means we don't have any interest in, so we have interest in rotation like this. Like I'm going in a circle. You can think of that as a rotation. We have interest in that. We'll do a thing on circular motion, but we don't have any interest in this. Okay? So the difference is here I'm taking different spots in a circle. The one that we don't care about for now is changing orientation. Okay. So horizontal motion of an object doesn't change gravity's effect on the object. Okay, so the third one is the one that says when two things are in contact, and in contact, like when two things are pushing on each other, well, let's say, so anytime two objects are in contact, they apply the same size force to each other. So the examples I gave last time all had to do with sort of short duration collisions, but you can also imagine, two like sumo wrestlers or whatever, where one's way better than the other one, and you have a thing where over a couple of seconds or whatever, one person's just pushing the other one straight back, the other one's falling back, and this one's just pushing forward. But the forces that they're exerting on each other still have the exact same size. The difference is that one person is able to deal with that size force with what they're doing with their legs and whatever, and possibly has more mass, which helps a little bit. And the other person isn't able to, exert a force on the ground that can counteract that contact force. Okay. Of all of these, this is the weirdest one. This is the one that you're like, that doesn't make any sense. And then later you think, okay, I get it. And then you go back to it not making any sense and then getting it. And little by little, it's like, it's a longer period of time between times you're confused about it until finally, it goes away. But by then you're not interested anymore. Because you're like 50. 50 isn't as old as it used to be. And then the last one, anyone remember what the last one was? Do I? Yes, that's what it was. Yes. So, anybody want to? I cut you off because I got so excited. Yes. So, well, you're on the right path, but and we haven't talked about what velocity is yet. But really, speed is what I said, and speed and velocity we're going to see are two different things because velocity includes directional information. Speed doesn't. The speedometer on your car doesn't tell you which direction you're going. If you're going 50 miles an hour north, that's the same as 50 miles an hour south. Velocity, we'll see how, includes that directional information. So this last one is, so in 1D, this isn't true. But once you get to 2D or 3D, objects can be accelerating even if their speed is constant. Um, and that's because if your direction is changing, you're accelerating. So any kind of turning is an acceleration. Um, so like when I was in driver's training, they said when you're going around a turn, you should accelerate into the turn. And I wish I had been like, duh, it's accelerating just because you're turning. I'm already doing that. Like with a Napoleon Dynamite voice. He would have thought that was funny. He wouldn't have back then because Napoleon Dynamite hadn't come out. Okay, any questions about any of those? All right, so let's go on to units and unit conversions. Well, so units or unit conversions and scientific notation. And this is the stuff we need to discuss so that you can do the problems that that I listed as an assignment on D2L. And just a reminder about those assignments, you're not going to turn them in. So there's, you don't have to have it finished by Monday or anything like that. But it's the only way to get ready for the exams is doing those problems. And if you can stay more or less on the pace that I'm assigning them, you'll be happy, because if you start to get behind, you're going to have a lot of work to get ready as you get close to one of the exams. And it works better if you do sort of a slow soak on the material anyways, instead of trying to cram. Did everyone see that assignment? So so in the announcements, I'll list some problems to do, like, and from what set, and then you go to the content and, pull up. So I think the way it's listed, it says what notes to read for the day. And then it says the assignment is units 1 through 10 or something like that. And so you go to content, go to the practice problems, and then under units, you do those first 10 problems. That's the way that's supposed to work. And then on Monday, I'll start class with, answering any homework questions that anyone has, things that were confusing or whatever. But I strongly recommend that you try to stay caught up with those, because each class period I'll give a new set of problems to do. Okay. All right, so every physics measurement you take has units. If you're asked what the distance is across the room, you can't just say 15, it doesn't make any sense unless you say 15 of what amount, and all units that we're going to use in this class are combinations. Well, they can be individual ones, but either, so all units in this class are made up of 3 basic unit types. And those are length, time, and mass. If you take Physics 2 next semester, you'll see that there's also a unit charge that isn't made up of any of these, but we're not going to deal with electricity in this class, so this is good for us. And so, like, for example, the units of speed or velocity are a length divided by a time. So even though velocity isn't listed in these three basic types, you can make the units for velocity out of those three. That's what I mean by can be made up of those. In SI units, a lot of people call SI units Standard International. What it really stands for is a French thing, Système International. I know you have to like throw out some syllables here and there in French. So it's something like this, Système Inter, and I don't know how to spell the rest. But it's the international system of units, and length is meters. That's abbreviated with a lowercase m. Time is seconds. That's a lowercase s. And mass is kilograms. Wait. Time is seconds. And mass is kilograms. And that's abbreviated lowercase kg. And so SI units for speed or velocity are meters per second. And one of the things that we're going to have to be able to do is go back and forth between units of the same type, but in different systems. So you might get a speed in feet per minute. And since we want to do calculations most of the time in SI units, we'd have to convert from feet per minute into meters per second. So this is sort of the idea. So for any measurement, including units, think of that measurement as a number times one of these unit things. You know, like if you figure out that from here to here is 10 meters, you know, what that means, it sort of makes sense if you think about what it means to think of that as a multiplication. You're going to take the number 10 and you're going to have 10 of these 1 meter units. So there's 1, 2, 3, you know. So any measurement including units think of that as a number times the unit. And that's going to be important when we start doing the conversions. So let's say, for example, you want to know, I'll say it this way. Let's say that you want to convert 3.5 feet to inches. We're going to think of 3.5 feet as 3.5 times this unit feet. Okay. And we're going to use the conversion factor that says 1 foot is equal to 12 inches. Since those two expressions mean the same thing, 1 foot and 12 inches, we can divide one by the other one. And since you're dividing one thing by itself, you just get 1 when you divide them. And so 1 foot divided by 12 inches is equal to 1. And that's also equal to the reciprocal of that fraction. So it's the same thing as 12 inches over 1 foot. And so now to do the conversion, I'm going to multiply our original quantity, 3.5 feet, by one of these two fractions. Okay? It's okay to do that. We're not going to change what that original quantity means because those fractions are both equal to 1. You can multiply anything by 1 without changing what it is, right? That's kind of the nature, the main thing about 1. So we're going to start with 3.5 times feet. And I'm going to multiply this by, I'm going to use this one, and I'll talk about why after this. So I'm going to multiply it by 12 inches over 1 times feet. And now you can think of those units as just algebraic variables. They obey all the same mathematical rules. So if you have this unit of feet in the numerator and you have it in the denominator, you can cancel those. After you do that, the only units that are left are inches. So that's good. That's what we want. And the numbers, we have a 3.5 times a 12 divided by 1. And so multiply and divide out the numbers. Your units are inches, and you get that 3.5 feet is equal to 42 inches. And that's the answer we want. Okay, so the next question that comes up sort of naturally is, okay, this worked, but we had two options for the fraction to multiply by. So how do we know we want to multiply that original quantity of 3.5 feet times 12 inches over 1 foot? What if we multiplied by 1 foot over 12 inches? Would it work out the same? So let's go through that. So what if instead we had multiplied by 1 foot over 12 inches? Okay, so to do that, we're still going to start with 3.5 feet. And now we're going to multiply by 1 foot divided by 12 inches. And this time we don't get the cancellations of the feet. We end up with 3.5 times 1 divided by 12 for the number. That's like 0.2916 repeating. And then the units we get are feet times feet over inches. Or you can think of that as feet squared over inches. So is this answer wrong? It's wrong in the sense that what we were asked to do was convert into units of inches, and we converted into units of feet squared over inches. That actually is a unit you could use. No one would ever do it because it's, unnecessarily complicated, but there's nothing wrong about that answer. We just don't have the units we want, okay? So to get the units, so this is not what we wanted. So what you always want to do is choose the fraction that's going to cancel out your unwanted units. Okay, there's always a unit in the original quantity, at least one, that you don't want to be there anymore, and you need to choose the fraction that's going to make that cancel. So choose the fraction that cancels the unwanted units. So if you go back up to the example that worked out the way we wanted it to, started out with, you can think of 3.5 feet. I think for a lot of people, it's easier if you think of everything as a fraction to start with. So you can think of this as just divided by the number 1. And then you have a numerator and a denominator. Okay. The units that you want to cancel are the feet. You want to get rid of those. And feet is in the numerator. So you want to choose the one of these two fractions that has feet in the denominator. Okay. So if you think of it that way, the one that you want to choose has to be 12 inches over 1 foot. Okay. Any questions about that? And just one short little thing to add on to this. I'm going to use this shorthand notation. You can use this or not. It saves a couple of pen strokes is all. But the shorthand notation that I'm going to use is what I wrote up here as 3.5 feet times 12 inches divided by 1 foot. I'm going to write that as a big fraction bar. And where I would have parentheses separating things, I'm just going to write a vertical line. If you've taken chemistry before, I would guess you've probably seen this. So 3.5 feet, and then that's multiplied by, I have the 12 inches over here and the 1 foot over here. And the math works just the same. I'm just saving a couple of things that I have to write down every time. Any questions about that? Okay. So next, let's say that we want to express the quantity 61 miles per hour in meters per second. And the conversions we want to use are that we know 1 mile is 1,609.344 meters. And 1 hour is 3,600 seconds. Okay, so just like I did before, I'm going to start out with the given quantity. So we have 61. I'll write it as miles in the numerator and hours in the denominator. And this time, so in the first example I did, there was just one step we had to take. Here it is. So we just had to take the starting quantity, multiply by one fraction and we were done. This time we're going to have to do it in 2 steps, but you can do the whole thing in the same multiplication problem. You just have to have one thing multiplied by another thing multiplied by another thing. So I'm going to first do a multiplication that converts miles to meters. I know I'm going to use either 1 mile over 1609 meters or 1609 meters over 1 mile. And the way we know which one of those is the miles here in the numerator. For a fraction needs to have miles in the denominator to cancel. So do I want 1 mile over 1609 meters or 1609 meters over 1 mile? That was totally unintelligible, but I'm going to assume you said 1609.3. I'm going to assume you said 1 mile over this. Are you stupid? Just kidding. 1609 meters over 1 mile, because the mile in the denominator here cancels this mile here. Okay? Anybody have any questions about that? Okay, so 1609. If anyone ran the mile in high school, this is, it's 1600 meters in high school track. That's how short you were of running an actual mile. So 1609.344 meters over 1 mile. And if we do the cancellations, you can see that the miles here cancel. And so now the units that we have left, if you just look at all the units that aren't canceled out with anything, you have meters in the numerator and hours in the denominator. So the last thing we have to do is just convert from hours here into seconds. Okay, so now we know we're going to either multiply, so we're going to multiply some other fraction here, and it's either going to be 1 hour over 3,600 seconds or 3,600 seconds over 1 hour. And the one that we choose has to cancel this hour that this time is in the denominator. Okay? So we want the fraction that has the hours in the numerator, in the top. Okay? So this time I'm going to multiply by 1 hour over 3,600 seconds. And if you do the cancellations, you have an hour here that cancels with an hour there. And the only units that are left are meters on the top and seconds in the bottom. So that's what we want. And so now we know all we have to do is just multiply those numbers out. And you get 27.26 meters per second. Any questions about that? Okay, so this is a case where the units we're using aren't one of those just basic types by themselves. They're, some combination of multiplied basic units. And whenever you have that, you have to do it in multiple steps like this. Yes? Oh, yeah, good question. No, I don't care about sig figs. I know, like, when you did take chemistry or when you do end up taking chemistry, they're going to be obsessive about that. So that makes me feel comfortable saying just round off as much as you want. Yeah, it's not really a philosophical thing. It's just like, I'm going to save time because I know someone else is going to make you do that later. So. Any other questions? There was one other person, right? Okay. All right, so let's do another one. Actually, let me write one up here, and why don't you take a little time to try to work through it with each other? You can ask me questions if you get stuck, um, but let's just see if you can sort of make sense out of this. So let's say um, convert 10, what are we going to do here? Kilogram meters per second into, now what did I do? Let's turn this into, oh Lord. Okay, no, don't do this yet. I'll give you another one later to do. Okay, so let's convert 38,640 yards per minute squared into meters per second squared. And what we want to use this time, I guess I'm going to show sort of two things with this one. So let's say that we don't happen to know, that's not really a thing anymore because you have your phone, but let's say that you know that there are 3 feet in a yard. So 1 yard is equal to 3 feet. But we don't want feet either. So let's say that we also happen to know that 1 meter is 3.281 feet. And then we know that 1 minute is 60 seconds. Okay, so to do this conversion, we're going to have to multiply by a fraction that converts this yards into feet, then multiply by another one that converts the feet into meters, and then multiply by another one, then we have to deal with the fact that we're going from minutes to seconds. The other thing that we didn't see yet that is coming up in this one is we have an integer exponent on one of these units, okay? And the way we're going to approach that is we're first going to expand this out into 38,640 yards per minute times minute, okay? And then that'll remind us that we have to, it's not enough to just cancel one of those minutes. We have to do it 2 times to cancel the both, okay? This is also maybe a good time to say, for any of you who've done a lot of this kind of stuff and you have ways that work for you, that's fine. You don't have to approach these the way I do it. I'm trying to, for the people who haven't seen this or aren't comfortable with this, I'm trying to give a way that makes good sense, that's easy to follow. But if you have your own way, feel free. Okay. All right. So the starting quantity is 38,000 640 yards. That's in the numerator. And then in the denominator, we have minutes times minutes. If you have any questions, feel free to ask anytime. So I'm going to first convert yards to feet and then feet to meters. To go from yards to feet, I'm going to use either this over this or this over this. Do I want the yards to be in the top or the bottom when I multiply? Yeah, I want it to be in the bottom to cancel the yards here in the top. So we have 3 feet over 1 yard. And I'm going to just sort of, you don't have to do this as you go, but for now, I'm going to just do the cancellations as they come up. So this yard cancels this one. And so now the units of length, the feet are, feet are the units of length that we would have if we multiplied it out. And now we want to go from feet to meters. So we're either going to multiply by 1 meter over 3.281 feet or 3.281 feet over 1 meter. Do we want the feet in the numerator or the denominator? Yeah. So we want to cancel these feet. Those are the unwanted unit now. So we have 1 meter over 3.281 feet. And if I do that cancellation, now the units of length that we have left are meters. And now I'm going to start to cancel these minutes. We have 2 of them. So we're either going to multiply by 1 minute over 60 seconds or 60 seconds over 1 minute. Which one of those do we want? Yeah, we want the minutes on top to cancel the original minutes that we have on the bottom. So 1 minute is on top. And 60 seconds is on the bottom. And then we cancel one of these with that. But we still have, if you look at just the things that aren't canceled yet, one of our time units is still minutes. We don't want that. So we have to go through this one more time. So we'll multiply again by 1 minute over 60 seconds. And that cancels this and this minute. And finally, we have units of meters per second squared. And then you just have to multiply it all out. And you get 9 point, I think actually you don't get this because I rounded some of this stuff off, but what I wanted to get was 9.81 meters per second squared. And I wanted this to be, so this is the first time that you see this important quantity that's going to play a big role in this class. That is the acceleration of objects in free fall. And you're like, well, what objects? And I'm like, it doesn't matter because no matter what the weight of the object is, if we ignore the effect of air resistance, everything falls the same, everything accelerates the same due to gravity. Any questions about that example? Okay, so now let me give an example, see if you can think through this one. So let's convert 1 cubic meter into cubic centimeters, given that 1 meter is 100 centimeters. Okay, so feel free to talk to each other about it, compare answers as you go, compare approaches, ask me questions if you get stuck. And then after I give you a couple minutes to think about this, I'll go through it. Okay, so we're going to start out with 1 meter times meter times meter. Okay, that's 1 cubic meter. And that's all in the numerator. And then we're going to multiply by either 1 meter over 100 centimeters or the reciprocal. We want the meters of our fraction to be in the denominator to cancel one of these. So 100 centimeters over 1 meter. And one of these cancels. And then you just have to do it 2 more times exactly the same to cancel the other 2 meters. So 100 centimeters over 1 meter, you cancel the second one. And then 100 centimeters over 1 meter to cancel the third one. And now the units you have left are centimeters cubed, so that worked out. And now we just have to multiply the numbers together. 100 times 100 times 100 is 1,000,000. So 1,000,000 cubic centimeters. And so this big box, I don't know, this is the best way I have to visualize what 1,000,000 is. It actually is sort of surprising to me, but that's how it is. This big box that's this wide, this long, and this tall, you can fit 1,000,000 little 1 centimeter cubes inside there. Yeah. Oh. Well, you know, that's a good example, I would say, of like why it's better if you don't make stupid mistakes, because then I have to like guess, you know, like, is this a real thing or is this, you know what I mean? So you're better off just taking a little more time and getting it right. But if you wrote this and then multiplied it and gave the answer as 300, I would give you full credit. But I probably like texted around to people in the department. Any other questions? Okay. So the next thing is scientific notation. And the idea of scientific notation is any number can be written as plus or minus, so the sign stays the same in either of these formats. But then one non-zero digit and then a decimal point, and then a decimal, and that can be any number of decimal places that you feel are important, you know, times 10 to some integer. And those integers can be positive or negative. So for example, negative 3481 written in scientific notation is negative 3.481 times 10 to the third. And 0.0036 can be written as 3.6 times 10 to the negative third. And so what we need to be able to do is go back and forth between standard notation and scientific notation. Like, what's the purpose of scientific notation? I guess the main purpose is that when you're dealing with very large numbers or very small numbers, it makes it a lot easier to write it. Like, if you're talking about the length in meters of an atom or something, you have a lot of zeros you have to write after the decimal before you get to the thing. And every time you write, if you're writing more than 10 zeros, you can imagine it's very easy to miscount or for the person reading it to miscount. This sort of eliminates that problem. And it's the same thing if you have really big numbers, like the mass of the Earth is something times 10 to the 24th kilograms. So you'd sit there forever writing zeros. This is just a nice, concise way of writing big numbers like that. And one other thing I wanted to say, so in this class, significant figures isn't going to be a big deal. You don't have to worry about that at all. But if you remember people who've taken classes with significant figures, you learn everything in terms of these rules and, multiplication, division and stuff, that has its own rules, and this doesn't solve that problem. But you learn these rules that's like, how do you know how many significant figures a number has? And it's like, okay, well, do you count zeros? Okay, well, it depends. You count any zeros after the decimal place, but you don't count any zeros that lead right up to the decimal. You know what I'm talking about? I don't remember what the rules are. I'm just sort of trying to like imagine it right now. But if the numbers are written in scientific notation, you never have to worry about that stuff because the number of significant figures you have is just all the digits before the times 10 to whatever. Okay? So like this, I think this one's a good example. Do you count those? Are those zeros significant figures or not? I can't, well, write it in scientific notation. And then 1, 2, you have 2 significant figures. And you don't have to think through, those rules are just also wordy. This is just a nice, concise way to remember that. Okay, so we need a method to go from standard notation to scientific, and a method to go from scientific notation to standard. So we have 2 of these methods. For going between standard and scientific notation. And just like with unit conversions, if you have a way of thinking about this that you're comfortable with, feel free to keep doing it that way. Later in the class, there will be things that I want you to do in a specific way, but all of the stuff we've talked about today, if you're comfortable doing it, keep doing it like you are. But if you are not comfortable with this stuff, the approaches I'm giving you are, they work, and I think they're pretty reasonable. Okay, so first let's do how you go from standard to scientific notation. And I'm going to do this with the number as an example as I go, negative 541.6. So the first step is count the number of places, and this number I'm going to call n, capital N, that you have to move the decimal point left or right so that you have one non-zero leading digit. Okay, so in the example, to have one leading non-zero digit, we have to move two decimal point 2 places to the left. Okay. So n is equal to 2. And we have to move to the left. And once you've done that, if you went to the left, then you're going to have times 10 to the positive n. And if you move to the right, you're going to have times 10 to the negative n. Okay, so when we move that decimal place 2 spaces to the left, we ended up with negative 5.416. And n was equal to 2, and we moved to the left, so this is going to be times 10 to the positive second power. Any questions about that? And then the second thing we have to be able to do is to take a number in scientific notation and express it in standard notation. So go from scientific to standard. And this example, I'm going to use 6.52 times 10 to the minus 4th power. So the first thing you're going to do is read the absolute value of the power. And we'll call that one n, capital N. So in the example I have here, n is equal to 4. And then if the power is positive, move the decimal point n places to the right. And if the power is negative, move the decimal point n places to the left. Okay, so we started with this number 6.52 times 10 to the minus fourth. And we figured out that n was equal to 4, and the sign of it is negative. So I'm going to write my, so here's the 6, 5, and 2. And we're starting with the decimal point right after the 6. So I'm going to start here. And since our n is 4 and the power was negative, I'm going to move the decimal point n places to the left. So I'm going to start here and go 1, 2, 3, 4, and there's the decimal point. And all those gaps have to be filled in with zeros. And so there's the answer. Any questions about that? And you know, here's another example. Like, you look at this, if it was more than a year ago that you studied significant figures and someone asked you how many significant figures there are, I think for a lot of people, oh God, what's the, you know, what do we do with these zeros? You know, like there's just this wordy description of it. But if you write that in scientific notation, then it's just 6.52 times whatever, 652, 3 significant figures. Okay, the last thing that I need to talk about today is prefixes for units, like kilo and deca and that kind of stuff. So prefixes for units. So for example, kilometer or microsecond or, well, I can't think of any more. Maybe those are the only two. Millimeter. So there are basically like 5 important prefixes for us. There are a lot more than that, but those are the ones that we're going to use in this class a lot. And so first I want to just list out what they mean. So from smallest to largest that we'll see a lot, micro is represented with the Greek letter mu. It can be hard to remember a lot of Greek letters, but this one is easy to remember if you remember that symbol is like a cross between an M and a U, and that's how you spell mu, M-U. And micro, anytime you see this mu, you can think of that as meaning times 10 to the minus 6. And then the next one is milli, M-I-L-L-I. That's represented with a lowercase m. And anytime you see that lowercase m, you can think of that as meaning times 10 to the minus third. And then centi, that's abbreviated with a lowercase c, and that means times 10 to the minus second. And then for the ones bigger than 1, kilo is a lowercase k, and that means times 10 to the positive third. And then mega is capital M, and that means times 10 to the 6th. And I guess now with computers, you know, as computers keep getting faster, we get more and more used to dealing with the bigger ones of these. You know, we're used to nanoseconds and gigabytes and terabytes and stuff like that. But you can look up those if you want other ones, but those are the ones we're going to see the most. And there are kind of two things that we need to be able to do with these. We need to be able to go from an expression that has one of these prefixes in it to one that doesn't. And we need to be able to go from things that don't have prefixes in them to ones that do. Okay, so the first one, so if we're going from something with a prefix to something without, for this, you can just substitute in the, just take out the prefix and replace it with the times 10 to whatever. So, like for example, if we're going, so for example, how many meters are there in 17.5 kilometers? So our starting value is 17.5 kilometers. And so we'll start with that. And we'll just replace that lowercase k with times 10 to the third, because that's what kilo means. And then we still have the meters. And so this is equal to 17.5 times 10 to the third meters. So that's easy. And then this, I have that written in something that's not really scientific notation and it's not really standard notation. So, but probably most of your calculators, if you punch that in, would give you one of those other formats. So, but this is 1.75 times 10 to the fourth meters. And then if you're going from no prefix to something with a prefix, well, in this case, you can't just substitute in for the prefix because you don't have one to start with. So this one you have to do more like a conversion. Okay, so for example, let's say how many microns are there? Micron is a micrometer. So how many of these are there in 0.20 meters? Okay, so our starting quantity doesn't have a prefix in it, and we want to go, convert to something that has one. So the way we want to do this is we're going to use the definition of that prefix to give a conversion factor, and then we'll just do it like a unit conversion. So we know that 1 micron is 1 times 10 to the minus 6 meters. I did that just by replacing the micron, the mu, with times 10 to the 6. And now we have our conversion factor. And now we can say 0.20 meters. We'll multiply it by 1 micron over 1 times 10 to the minus 6 meters. These meters cancel, and you get 200,000 microns. Any questions about that? Okay. Well, that's all for today. So see if you can get through those problems. We don't have class until Monday, but if you email me about it, I can probably, answer questions over email. And I think I mentioned we don't have lab this week because we didn't have class. We didn't have lab on Monday. But if anybody wants to stay around and ask questions or anything, I'd be happy to stay and do that as long as you want. So, all right. Have a good weekend.